My name is David Baum. I'm a senior engineer at OnBackup, and today I want to talk about async and await. What the hell is async and await? What is async and await in Python? So that's our next half an hour. A bit about OnBackup. OnBackup is a SaaS provider handling data of our customers on other SaaS providers. It's a great place to work for. We are always growing. We are always expanding. So come work with us. It will be worth your while. What's async and await? Async and await is basically a model for concurrency. When we're talking about concurrency, we're talking about doing stuff simultaneously, running things in parallel or in tandem to one another. In this supermarket example, there are many customers. Each customer wants to be served, so the supermarket offers many cashiers, many checkout places. So actually, many customers are being served at the same time. So this is one model of concurrency. This is the multi-threaded model of concurrency, right? Many execution units running in parallel, okay? And this is kind of the standard model of achieving concurrency. But we can contrast it with another model of concurrency, which is the async-await model. So async and await is a model of cooperative multitasking. I'll explain this in a minute. Basically, it's all the hype because of JavaScript. When people are talking about the great performance, the V8 performance in the browser, in Chrome or wherever, there's under the hood what's called UVlib, which is basically this, an async and await framework, a great one. And we can sum up this framework, which we'll present in a moment, in an event loop plus a single thread. So it's a single thread being driven by an event loop. And it's been around ages in Python since 2015, that's Python 3.5. So it's a mature technology in Python, something like 7, 8 years old, and we're going to present it now. Okay, so in order to explain the async await model of concurrency, I chose this image from the Israeli post office. This is a classic Israeli line. So as you know, there's the normal line like in England or I don't know, US and Germany, where you just wait and wait and wait. And then when you finally reach the counter, you're being served and you're the only one being served by that particular clerk. But we can see something interesting in this image. There's, if you can see, there's window number 3. There's a family there. There's a woman with 2 kids. But there's another woman standing there on window number 4, and she clearly wants to be served by that same person while she's not standing in line. So how this works, you all know that. You reach to the clerk, and then sometimes she tells you, oh, you didn't fill out this and that form, and she tells you, take this form. And the person behind you will say, if you're waiting, can you just serve me? Can you help me? And if the family on the front would yield their control of the clerk, of the ledge, then they will move to the side, okay, and you will be served. And then the person behind you can do the same shtick, right? If you're filling out forms, you're kind of resting, they will say, I just need to change money, can you help me? And then we have this other model of concurrency where you have one execution unit, the clerk, but she's serving multiple persons or multiple execution contexts in the same time frame, not really in the same single moment, but kind of concurrently. So this is async and await, the model at least. Okay, so why do we want to async await? What's wrong with the threaded model, with the many cashiers kind of model? A true story, at OnBackup we're kind of a successful startup, and we've been fortunate enough to build a product which was successful, and then another product, and then another product. And at some point we kind of figured out that we've got a big monolith. And like most companies finding out that you've got a monolith in your hands, we chose the microservice way. This is actually like an architectural diagram of a product being developed at our group. It's a sketch of it. It's been changed a bit. But the whole point of this diagram is that you've got many services. They are called microservices for a point, for a reason. They are microservices. Each service is doing a bit of load, a bit of work. And it's basically taking something from sending a request to another service, waiting on that other service. Maybe it's a database, maybe it's a Redis cache, maybe it's an identity provider, and in the meantime, the microservice waits. And it waits for hundreds of requests it sent, okay? We're handling hundreds of requests, thousands of requests each moment, and basically each of the requests is doing nothing. It's idling. It's filling out forms on the side of the clerk, okay? It's not really taking up the CPU time, which means that in the world of microservices, the async-await model, the model of I want to budge in and maybe yield control if I'm not doing anything, is a relevant model, and we would like to consider it. So to sum up the why async and await, I haven't spoken about it, but we live in, well, I said we live in IO-bound worlds, but the thing is that Python threads are really bad. I think the last speaker spoke about the GIL. Who, by a show of hands, has heard about the GIL? Yeah, so like 100% of the room. So as you know, true concurrency is not really possible in Python. This is, by the way, not really true for IO. IO actually works concurrently in Python because it drops the GIL. But if you want to run multiple pieces of Python code in true parallelism, you can't do that. So threads won't help you at all. So on the one hand, it's really, you don't get the performance. And on the other hand, something that we don't think about when we think about threads is the overhead of trying to coordinate different threads. So on the basic level of things, if different threads are sharing a resource, maybe it's a dictionary or an array or a list or whatever it will be, they can step on each other's way. Because if we'll go back to the post office example, the multi-threaded way of doing concurrency actually means that the guy, the security guy on the front, every 20 milliseconds come to another person being served and just yanks that person out of the ledge, puts this person back to the line, and puts another person on that ledge, which means that somebody can find itself filling out the wrong forms. Okay, you reach a ledge, but you're filling out the forms of the last guy. Okay, so if we are in the multi-threaded world, we need to take extra steps to coordinate our shared resources. This can be a lock usually, or maybe a condition variable, or a semaphore, or some kind of other synchronization primitives. And this is an overhead for the programmer and also hurts our performance. So we should really consider async await. Okay, so now this is kind of a two-part talk. This was the intro. Now we'll see code. The examples I will show are taken, they're kind of a rehash and adjustment of a long article, actually a whole book chapter written by Jesse Davis, formerly of MongoDB, and Guido van Rossum. It's on GitHub if you want to kind of delve into it. It's really good. So most of our examples are taken from there. Okay. Good, so now we'll move to Python. Okay, so we've got a server running somewhere in the world and we want to send it some request. Okay, we sent a request. It's a kind of a feed server, okay? A very known phenomena. Maybe it's a Twitter feed or something like that. So we are sending a request. Everything is good. And now what we want to do, we want to implement a simple GET request with our own bare hands. So we'll do that. Okay, so this is the kind of the construct of a very basic GET request. It has a host, a port, and a path it wants to reach. And it's really simple. You just create a socket. Socket is the most basic primitive for networking. Whenever you open a new connection in a request or URL-lib or whichever tool you've got, you basically have a new socket on your hand in the underlying lib. So we're creating a socket, we're connecting to it, we're sending the request, receiving data, returning it, all good. So let's run this. This is actually, if you don't want to use request, there you go. You've programmed your first HTTP request. So let's run this. I'll enlarge the font. Yes, okay, so actually I want it to run 5 times. 1 moment. Yeah. Yeah, okay, great. So here we just sent 5 requests to this unknown server somewhere in the world, and it went happily. But now, our whole point of this exercise is to build our own async and await framework. For an async and await framework, we need to not block. We don't want to wait, okay? We want to be able to step aside if you're just filling forms. If you're waiting for another microservice, we don't want to block the execution context, the thread. So maybe we should consider using non-blocking sockets. So this is the non-blocking version of that same code. I'll remove this connect. Same code, but now we told it to be non-blocking, and we even caught the exception of the connection because we don't care if the socket is not ready. Let's run this and see how it works. Okay, and it doesn't work. It says socket not connected, which makes sense. We asked the socket to be non-blocking, and now we're trying to use it, but it's not ready yet. So let's see what can we do to change this socket and achieve our goal. Okay. Cool. Yeah. So we've got that same code. We've got the non-blocking code, right? But we've sprinkled a lot of these yields and the register. The selector register. I would explain both of them, but I want to digress for one moment and talk about generators in Python. I'm sure you all know them, but I want to kind of show them. Yeah, so this is let's program a simple generator. We call it gen. It gets a number, and then I don't know. Let's say we set the number to be 0, and then we do while current is not 0. Yes. Then I don't know. Just yield current. Maybe we can even print current. Never mind. We'll print it afterwards. And we want to current plus plus. Okay, so we've got our own generator, something that we all know. And then if we kind of run it, let's generate some 3 numbers. Nothing seems to happen, right? I mean, but we've launched the code. But as we are familiar with, I'm sure G is actually not a function. It's an object, and it's what's called a generator object. For a generator object to work, we need to run it, okay? We need to drive it. It's like a car needs to be driven, so we just next it, okay? So here we go, and it produces the output is small, but yeah, 0, 1, 2, and eventually it will tell us stop iteration, the generator is consumed. And the reason that I wanted to talk a bit, to digress to generators, is because generators are a really cool thing. They allow us to maintain state. Have you ever thought about what happens to this code? It yielded the number 2, and then, okay, how does it know how to return to the same place? And we're going to use that trick. It's going to be hairy because I don't have a lot of time, but we're going to use that same trick to enable us to have our own async and await framework. So we've got the same code, but now we are yielding each and every time that we're waiting for some network event. And if you'd look, we have used the selector model. The selector model is kind of like a networking primitive model provided to us by the OS in Windows, in OS X, Linux, Mac, wherever. And we can tell this model, dear selector model, please take this socket, this connection, and when it's writable, call me, bring me something. And so this is what we are doing. And now I want to kind of move ahead to our full framework. Yes. Okay. Now we get that same get, but we want to introduce two synchronization classes. We are introducing the class of future. Future is a very known class. It exists in JavaScript. It's called promises. In Python now, it's part of the standard library. But a future is a very simple thing. It's just a promise for something to be fulfilled in the future, okay? It's like an eventual thing. And here we've got another class. It's called a task. A task is basically the driver for a generator of this kind of classes that we are running, like the coroutine that we saw earlier, the get with the yield. It's basically a generator. So we need someone to drive it, right? We want to next it whenever it's ready. And I want to demonstrate how we can have a whole framework just using this kind of method. So this is the complete multi-connection get async and await framework. We've got that same socket, but now we are creating this weird future object, which basically doesn't do too much. We're doing the same. We're registering on the selector model, telling him it whenever the socket becomes writable, so we can send something down the line, produce to the caller the future. Okay, give the caller the future object, and then we just yield, and we do the same trick wherever we think we need to yield control of our method to the networking. And if we look at the event loop, the driver that will drive all those things, then the event loop is really a simple thing. Here we are launching a bunch of tasks, a bunch of get tasks. These are the same get that we just saw. And now, while true, we're just taking an event from the selector, and we're just resolving the future, because we know that every event that will be yielded is a future object that we can retrieve. And so I first want to demonstrate it, and then kind of maybe delve a bit deeper if we have time. So let's run it. Yeah, okay, so we've just sent out like 200 requests. All these requests were interleaved. None of them was blocking. And we've just used a single thread, okay? Nowhere in our code, this is our entire code, nowhere in this code did we launch another thread. So kind of to wrap this up, I know this is kind of a very technical talk, and it's really hard to grasp the whole async-await framework in 20 minutes, but we do have a few takeaways, and here they are. Async and await is basically concurrency in a single thread. Okay, in a world that mostly waits, we don't want the hassle of being multi-threaded, and it's a really good. It's really good for us to consider the async and await model. It's a saner code model. Why is it a saner code model? So why is it a saner code model? Because whenever our code runs between two awaits or between two yields, we are promised no other thread will step on our common data structures, right? Because there isn't any other thread, okay? We are single-threaded. It is much more performant than threads. Threads are kind of heavyweight structures. They are OS structures. Every Python thread is mirrored by a single OS thread, so it's heavy both on the interpreter and the OS. And as we spoke about before, the GIL will kill your performance when you're talking about Python code. The network code actually will work the same, but the Python code will be killed by the GIL. And it's the whole magic of any async-await framework, be it JavaScript or Python, is that the framework supplies a dedicated network implementation like we just saw. Okay, if you know that there is async.io in Python, it means that people actually went and implemented each and every networking primitive in the way that we saw, which interact directly with the event loop, like this. And it's pretty stable in Python. It's mature, it's 8 years old, and it's available both as async.io in the standard library. Every Python 3 point whatever has it. We have AIO HTTP, which replaces requests, and Fast API and Starlet. Okay, thank you. Thank you. If anyone has a question, I'm available for questions. No, because, okay, yeah. So what he's asking is the entire async.io framework developed in Python or in some underlying code. Most of it is developed in some underlying code, but it's reflected exactly like this code. So the socket, which we just used, is basically like a wrapper around the C socket. So the developer of async.io, they just did the same thing in C. Okay, that's the same thing. Thank you.